Thank you for having me. So a little bit about myself. I'm Björn Ruytenberg. I'm a master's student at TU Eindhoven in the Netherlands. I'm a teaching assistant for several graduate and undergraduate courses. And in my spare time, I'm a security researcher. My main interests are hardware security and sandboxing and virtualization in commonly used enterprise products, such as Adobe Flash. And Adobe Flash is what I'll be talking about today, starting with some of the Flash runtime basics. I'll be going through an outline of the Sandbox security architecture, and then quickly moving on to Flash exploitation. Two scenarios, one in which I'm going to escape the local sandbox, and one escaping the remote sandbox. And for each of these two, I'll be demonstrating several examples of leaking information, stealing local files, and stealing Windows user credentials. And finally, in light of recent efforts by various vendors to deprecate Flash, I'll be talking about Flash, its future, specifically the gaps that are being left open to exploit by current plans to deprecate Flash. So Adobe Flash, I'm sure you're all familiar with it. It's a plugin that runs inside your browser, but you can also use it to develop applications for a desktop or your mobile phone. And some of the use cases are web UI animations, but also streaming DRM-protected media, browser-based games, audio and video conferencing, and basically any general-purpose application that you can think of. And it's multi-platform, so it runs on all contemporary operating systems. So a Flash application starts with writing ActionScript code. And this ActionScript code compiles to what is called an SWF binary. Now, this binary can then be embedded in HTML pages, which is the most common use case. But it can also be embedded in PDFs, compiled help manuals, HTML help manuals. And most importantly, it can also be embedded in Office documents. Now, running a Flash application, if you're running a Flash application, it will run in one of these sandboxes, and today I'll be talking about the top two. Starting with the remote sandbox. The remote sandbox basically allows a Flash application to access remote servers, but it does not allow the Flash application to allow the local file system. Local-with-filesystem is the exact opposite. It allows accessing the local file system, but it does not allow accessing remote servers. So suppose you have a local file, like an HTML file embedding a Flash application, and you will try to open it. Then it will be running in the what is called local-with-filesystem sandbox. And if you have a look at the Adobe developer documentation, there are actually two definitions that are relevant here. So I'll briefly go through them. The first one defines the local-with-filesystem sandbox itself. And Adobe says this is the default sandbox for local files. SWF files in this sandbox may not contact the internet or any servers in any way. So pretty straightforward. But then there's another definition that is important here. Adobe, in this definition, Adobe defines what constitutes a local Flash application. So a local SWF file describes any file referenced by using the file protocol or a UNC path, which does not include an IP address or a qualifying domain. So here it's already starting to be a bit tricky, a bit wordy, and a bit ambiguous in a way. Especially this file protocol and this UNC path. What are those actually? And how does the exclusion of an IP address or qualifying domain affect the former two protocols? So I'll come back to those questions later. But first, if you've ever used Windows file sharing, you'll most likely be familiar with this screen. And what you're actually using under the hood is a protocol called Server Message Block, or SMB. And closely related to SMB is the Universal Naming Convention, or UNC. Now, UNC is a Windows concept to express SMB paths to, an SMB server. And these resources can be anything from shared files to devices and named pipes. And you can use any of these host identifiers, an IP address, a domain name, and what is called a NetBIOS host name, which originates from Windows networks. It's a type of name resolution. So if you take all this into account, of course, this raises the question, what paths are accepted by Flash? So let's have a look at some examples. The first one, would it be accepted by Flash? Well, no, because there's an IP address in there. The second one, someserver.com. No, because it's a domain name. The third one, intuitively you would say no, but the answer is yes. And this is only the case if you're referencing the local host name. So in this case, some PC. So the other scheme that's being accepted by Flash is the file URI, and if you want to have a look at the definition, you have to go back all the way to 1994. This is actually the entire RFC, and the most important bit is already on top. It says that the file URL scheme is used to designate files accessible on a particular host computer, but this scheme, unlike most other URL schemes, does not designate a resource that is universally accessible over the internet. So this is quite an interesting exception because below you already see there's a host identifier in there. But it turns out that because the RFC does not specify which protocol should be used to fetch this resource, basically every implementation out there just ignores the host identifier and just assumes the path to be referencing the local file system. So here's an example on Windows, just a Word document hosted on the local C drive. And, well, apart from the former RFC, there's another one just highlighting some non-standard syntax variations. But that's pretty much it for the file URI. So in terms of Flash, Flash doesn't really impose any restrictions on the file URI under the assumption that you cannot express remote paths, so there's nothing to restrict. Okay, so if you want to escape the local sandbox, no, first let's summarize what we have so far. So we have the local-with-filesystem sandbox, and it lets us access UNC paths, and it lets us use the file schemes, but the Flash restricts UNC to local hosts only, and the file schemes takes only local paths. So the question is, if you want to escape the local sandbox, where do we go from here? Well, let's go back to path expressions on Windows. Flash is a multi-platform runtime, and on Windows it uses the Win32 shell API. Now, there's a book over here that I found, and it says Windows 2000, but it's actually much older. And it's quite an interesting API in the sense that it has a bag of tricks that you can use to do some interesting stuff. And one is that you can express UNC tags inside the file scheme. So in our example, we have this path to a remote resource in the UNC syntax. But if you want to express that in a file scheme, you simply add another slash swap forward and backslashes, and then include the entire UNC URL. Now, Flash actually parses this as being a local path. So for now, we can access remote resources from the local sandbox. So this is, of course, interesting. We just escaped the local sandbox, but we want to steal some files. So the approach is basically you append local file content to the SMB resource requests that you make. A couple of basic steps. So you read the file that you're interested in, and then you take into account some of the SMB path restrictions. So the file you're reading, you need to split in at most 260 bytes. And then URL encode whatever content it has. Then you append the chunks to all the SMB resource requests you're going to make. You make the requests, and on the attacker end, you capture all your requests and reassemble the entire file. So let's have a look how that works in practice. On the left, there's the attacker machine, and on the right, the victim machine. So first, I'll be running an SMB logger script that acts as an SMB server. And on the right side, the victim will be opening this very trustworthy-looking file. And as you can see, it reads the Windows host file and sends it in chunks to the attacker side. And as you can see, we reconstructed the entire file on the attacker end. Okay, so we can escape the local sandbox, we can exfiltrate local files, but there's something interesting going on here, because apparently we can access remote SMB servers. So for me, that triggered the question, can we actually leverage SMB for other kinds of attacks? So let's talk about SMB, in particularly SMB Authentication. SMB supports various authentication schemes, and one of them is called NTLM v2. And in this scheme, you log on user a username and a hash of the user password, and there's a challenge-response mechanism involved. So I'll briefly go through how that works. We have a user, and the user enters the username and password to log on to the Windows machine, and instructs the Windows client to connect to the server. Now, what will happen is the client will send a username in plain text to the server. The server will respond with a challenge, and the client will use this challenge to encrypt a hash of the user password and then send it back. Now, if everything went well, then basically the user will be authorized to access the resources on the server. Now, this seems or might seem a solid approach, but it is not really. There's an attack called the SMB Relay Attack, and again, I will briefly go through how this works. So the username logs onto the Windows machine, and then we'll try to access some resource on the server. But this time, there's an attacker in the middle. And so what will happen is the Windows client will send the username, and that means the attacker has the username. Now, the attacker will forward the username to the server, and the server will respond with a challenge, and that means the attacker has the challenge. Sorry, I'm moving too fast. The challenge will be forwarded to the client, and the client will use this to encrypt the hash of the password and then send it back. And that means that the attacker obtains the entire blob. Now, since the attacker already had the challenge, this means the attacker can trivially decrypt it and obtain the hash of the user password. This entire blob is then again forwarded to the server, and well, that basically means that the attacker can authenticate himself, impersonate himself as the victim. So the bottom line is the attacker actually obtains the plaintext username and the hash of the user password. So if you have this NTLM hash, what can you do with it? So first of all, you can mount what is called a pass-the-hash attack. One approach is that the attacker authenticates on the third-party host that the victim is allowed to access, and that's the scenario we've seen on the previous slide. One other approach is that the attacker authenticates on the client machine, but this was eventually patched by Microsoft. And the third option is that the attacker tries to authenticate against the remote desktop service, which interestingly does not work on Windows 10 because it got patched, but it never got patched on Windows 8.1 and Windows Server 2016, if I'm correct here. Now finally, if that all fails, you can try to obtain the plaintext password. And you can do that by using rainbow tables. You can also try to brute force the hash. And to give you a rough idea, basically an 8-character password permutation can be found in under 6 hours. And this is a number from 2012, so you can imagine that with today's hardware, it will be much faster than that. Right, so what does that mean for our attacker scenario? Well, we have our malicious Flash application running on the victim PC, so basically we can instruct it to connect to an SMB server of our choosing. So what we can do is run a Python script called SMB trap, and SMB trap is basically a Windows user credentials logger while acting as an SMB server. So going back to our attacker scenario, the application will try to connect to the attacker-controlled server, but there's something different this time, because Windows will try to authenticate as a guest. Now, obviously, this is not what we want, so we tell the client that it cannot access the resource without authenticating. And basically, this restores the regular logon procedure, which we've discussed in the previous slides, in the sense that the client sends the plaintext username to the server sends back a challenge, and then the client will send back a hash of the password encrypted with that challenge. So here's an example of how you can turn that into an actual attack. I'll be running SMB trap, and on the victim side, we'll be again opening a local file. This time we'll be opening it in Firefox. And as you can see, we just escaped the sandbox, and I put a rainbow table in there, so SMB trap managed to match the hash against this very secure password. So we can exfiltrate local files, we can disclose them to a remote server, and we can also steal Windows user credentials. So I've been having a look at how this is actually possible, and it just turns out there are a number of fundamental issues in sandbox policies. So starting with these arbitrary definitions of what constitutes a local file and what constitutes the local-with-filesystem sandbox. They are very wordy and very ambiguous, and apparently Adobe's developers didn't know what to do with it either. So that means that this blacklist approach does not cover all corner cases, like the examples I just showed. And it allows to turn remote paths actually into a local path. And so this renders Flash subject to well-known SMB vulnerabilities. Now, the interesting thing is this vulnerability is host environment agnostic. It worked in all browsers. And Chrome and Edge are actually two special cases here because they apply their own sandbox on top of the Flash sandbox. But despite this mechanism, the outgoing path, the path to that I created, was just being accepted as well. Now, it turns out that these sandbox policies were largely unmodified since Flash Player 9, which was released in 2006. So that means that this vulnerability has actually been present for over 10 years. It was fixed in Flash Player 23, and in this version, Adobe introduced new sandbox policies. Basically, they dropped the entire local-with-filesystem sandbox, and therefore also all the local file system APIs, because they had no use anymore. And local with networking became the new default sandbox, which is pretty much similar to the remote sandbox in the sense that you can access remote servers, but you cannot access the local file system. So this was a change that required web developers to refactor their existing applications. For local file system interaction, developers had to move to HTML5 techniques, which at the time was still being considered a competitor to Flash. And interestingly, it also covertly added some restrictions to SMB access in the other sandbox, the remote sandbox. And I'll be talking about that later. Okay, so here are the release notes for Flash Player 23. And, well, the new sandbox policies, they seem a solid approach, but there's no mentioning of this remote sandbox. So for me, this triggered the question, hey, would this sandbox be vulnerable, or would they have patched this vulnerability in the remote sandbox as well? So moving on to the remote sandbox, it turns out that they actually did change the remote sandbox. And, well, basically, the remote sandbox now rejects UNC and file style paths. And in fact, it rejects any URL which is being prefixed, not being prefixed by HTTP or HTTPS. So it turns out that Flash 23 actually introduced a whitelist approach. And so if you want to escape the remote sandbox, you have to think about other options. So let's go back to SMB. And back in 2015, there was a new publication on a new attack. And it basically works like this. You have an HTTP client, and it requests some file from a remote attacker-controlled server. And the server will respond with a 302 redirect header. But in the location header, it will not put another HTTP resource, but a reference to, well, the same kind of file style UNC path that I previously showed in the previous slide. So this vulnerability is actually well documented, and it turns out that it affects all of these Win32 API functions. So any application that uses any of these functions is actually vulnerable. And this triggered the industry to patch their software. So obviously, this triggered a question for me, is Adobe Flash vulnerable as well? So I tested for this using this setup, and I'll briefly go through how it works. We again have the client with our malicious Flash application. The client will try to download a file from the attacker-controlled server. The server will respond with an HTTP 302, referencing this file style UNC path. And then, if everything went well, the client will connect to our malicious SMB server. So the first try, it didn't really work. So here's a Wireshark trace, and we can see that while the Flash application is actually doing a request, there's no SMB traffic in there. But there are some other interesting things, like this thing on top. It says there's a GET request for a file called crossdomain.xml. This is pretty interesting because I didn't program my Flash application to do that. So it turns out that this crossdomain.xml is a reference to what is called the cross-domain policy file. And if you're familiar with HTTP cores, It's pretty similar in that it, well, in this case, it dictates when the SWF is allowed to load resources from a different domain other than the one it is hosted on. So, for example, if you have a Flash application and it's hosted on domain a.com, it will not be able to load any resources from domain b.com if domain b.com doesn't authorize the Flash application to do that. So again, here's Adobe's definition, and the most interesting thing is, apart from it being, again, very wordy, that there are also a lot of reference to domains. But what we're actually interested in is what happens when we're switching protocols, so redirecting from HTTP to SMB. Now, there's nothing in the spec that, that tells us why the attack is being blocked. But we do see that the Wireshark trace shows the cross-domain.xml being requested from the machine that is hosting the Flash application. So that is already contradicting the specification, but I figured, okay, you know what, let's just construct a least restrictive cross-domain policy. This is just a few lines of XML code telling the Flash application, it's okay, you can access any resource on this domain. And now I'm going to show you what happens when we feed that policy to the Flash runtime. So on the attacker side, I will be running two scripts. One is a web server, and the other one is SMB trap. And we'll be using Edge this time on the client machine, navigating to the web server. And as you can see, we've again escaped the remote sandbox and managed to obtain the user password on the attacker side. So this vulnerability actually broke Adobe's patch for the former vulnerability, and it exposes Windows user credentials to the remote server. And it turns out that, well, the problem basically is inconsistent path validation. This whitelist approach is seemingly very solid, but the check is only done once, and it's not being applied to any redirects. The interesting thing also is that it affects Firefox, Internet Explorer, and Microsoft Office, but not Chrome and Edge. And Chrome and Edge are probably not vulnerable as a response to the previous vulnerability. And for Chrome, we can actually see that this is the case. So Chrome has this nice developer tool called Net Internals. And we can actually see what happens when it processes the redirect response. And as you can see here, it does not take the redirect because it's being considered unsafe. So this vulnerability was fixed in Flash Player 26. And, well, basically it does so by applying input validation to redirects as well. The interesting thing is that it required, again, refactoring for existing Flash applications because it now drops support for SMB altogether. And also, it was a bit unfortunate that this change was not actually reflected in the change logs or the developer documentation. So, the future of Flash. I'm sure you've all seen this announcement back in August 2017 that Adobe is going to deprecate Flash by 2020. And so I figured it was a good idea to have a look at what the industry is doing to deprecate it. So from the browser perspectives, across the board we see all sorts of measures like vendor curated blacklists or whitelists, some form of click-to-play, and we also see that the plugin will basically be disabled by default at the end of this year, and plugin support will be dropped by early 2020 or late 2020 in some of the other cases. What is interesting, though, that Internet Explorer is an exception to this, because there are no restrictions to Flash until late of this year. In response to web browser vendors deprecating Flash, the web has moved to open web technologies. So for streaming, there's HTML5 video. For web UI animations, there's CSS and JS. Video conferencing, there's WebRTC. And for games and anything else, we have the Canvas, WebGL, and WebAssembly. And as we can see, this has actually resulted in a reduced market share from Flash, down from almost 26% in 2012 to 3.5% at the end of May of this year. Now, this obviously triggers the question, is Flash a thing of the past? Well, web browsers are not the only attack vector. In fact, Flash Player is distributed via mandatory Windows updates at least until 2020. There are no further announcements by Microsoft yet at this point. And this is especially a problem for Windows 10 and Windows Server 2016 and up, because you cannot opt out or uninstall Flash Player. On Windows 8.1 and Windows Server 2012 or 2, it's a little bit better, because you can actually uninstall Flash, but you will need to do so with each Flash Player updates. And as you can see in the screenshot right here, they do get released very occasionally. So basically, this means that the attack surface remains outside browsers. And one of the most important attack vectors here is Office, because Office does not restrict Flash content at all. From Office 2010 up to Office 2019. There's one minor exception. If you're running the Office 365 version, then you are protected. And as for the rest, well, you can embed SWFs in PDFs, in compiled HTML help files. And because Internet Explorer does not restrict Flash at all, well, basically, if you can get a hold of a Internet Explorer-based web browser control, you're back in business. And also, when you manage to invoke the Flash Player control through, for example, PowerShell or COM or the Windows scripting host. So the takeaway that I would like to give with this talk is that parsing seemingly simple input formats, such as, well, a file path, it can be, well, can be deceptively complicated, simply because of the diverse landscape of parameters that you have to take into account, like this URI scheme specs, which are very short and very, well, ambiguous in a way. There's OS-specific interpretations. So if you offload, for example, file path processing to the OS, then you need to be extra careful. There are sandbox policies that you need to take into account. If you're running inside a browser, then there's that. And also, well, the OS that you're developing for, it has specific vulnerabilities that you may or may not want to have a look at. So basically, you really need a structured approach for something as simple as parsing file paths to capture all corner cases. So all the issues, I disclosed them to Adobe. They were all patched. The deployment process was a bit unfortunate because it broke existing applications twice. Documentation was not updated. But the fix turns out to be a solid approach. The industry efforts to deprecate Flash, well, it generates mixed results. I mean, as we've seen, the web is migrating from Flash to other technologies. And most of the browser vendors are also deprecating Flash, but two other major attack vectors like Office and Internet Explorer are still vulnerable because they do not impose any restrictions. And, well, the fact that Windows issues mandatory Flash updates does not help either. So basically, the attack surface is still significant, and the advice I would like to give is regularly review the need for Flash Player deployment. And, well, disabling really is not enough. You really need to uninstall it. So if you're interested in the vulnerabilities, I've put up 2 blog posts with some more technical details. And I'll be around here at the conference, and you can also reach me on Twitter. Thank you. Any questions? No questions, I think.